We considered the case where the composite system is in a pure state. As an example, we had considered a pair of spins as a total system, or more generally, we have two systems A and B, and together they comprise a composite system. And we had considered so far the case where the composite system was in a pure state, and then we showed that, for a specific example, that even though the composite system is in a pure state, when we want to describe one of the subsystems with an effective state or a reduced state, then this reduced state may turn out to be mixed. It may well be that already the composite system is no longer in a pure state, but it's in a mixed state. So let us assume more generally that the composite system for A and B is already in a mixed state, rho AB. And as before, let's say that we are interested in the expectation value of an observable which relates to the subsystem A only. So the same situation as before with the two spins. The only way that we generalize that is that we say that the composite system is not necessarily in a pure state, but it may also be in an arbitrary mixed state. Again, if we ask, what is the expectation value of this observable? When a system is in a mixed state, we learned that the expectation value of an observable is given by the trace over the density matrix for the system times the observable. So in this case, we have to apply this rule. It's the trace of rho AB times XA. When we have composite systems, we always have to be careful about which Hilbert space we are in and where we take the trace. So rho AB is a density matrix in the total Hilbert space of the composite system. XA is an observable that relates to subsystem A only, and therefore it lives in the Hilbert space of subsystem A. One of you yesterday pointed out to me, and that's of course correct, that a more precise way of writing that, since we cannot simply multiply two objects that live in different spaces, to be more precise, we should say we have the observable XA that lives in the Hilbert space of subsystem A, and then we have to take the tensor product with the unit operator in Hilbert space of subsystem B. And now this tensor product is now an object that lives in the Hilbert space of the composite system, and then we may multiply that with rho AB and take the trace, and the trace is also defined in this composite Hilbert space. So to make this explicit, I would like to give a subscript also to the trace, indicating that we are taking the trace in the Hilbert space of the composite system. What's the definition of the trace? It's the sum of the diagonal elements in an orthonormal basis. So we take an orthonormal basis in our composite Hilbert space. We learned that the basis vectors in the composite Hilbert space are just the tensor products of the basis vectors of the individual Hilbert spaces. So the basis vectors have the form IA, JB, where again this notation is a shorthand for the tensor product, so it's IA tensor JB, and the IA are an orthonormal basis in the Hilbert space of subsystem A. The JB are an orthonormal basis in the Hilbert space of subsystem B, and their tensor product is an orthonormal basis in the composite Hilbert space. Okay, we said we have to take the sum of the diagonal elements, so we have here rho AB, then we have XA tensor unit operator, and then we have IA JB ket. Oh, and we sum over all the IA and the JB. Let me separate this into two distinct sums. So I have sum over IA, and then I have sum over JB. Let me also separate more clearly IA and JB. Then we have the rho AB. Okay, and then we have the XA tensor product with the unit operator. We learned when we discussed the basic rules and structure of a composite Hilbert space, when we have a tensor product of operators acting on a tensor product of states, then the operators act individually on the respective vectors in their associated Hilbert space. So we have the XA acting on the IA, and we have the unit operator acting on the JB. It doesn't hurt if I exchange the order of A and B as long as I keep the subscript. Yeah, so I can also write it in this order, JB. In this form I make clear this is a vector in the B Hilbert space. And then I have, and the unit operator acting on JB is just JB. And then I have XA IA. And then I can say this object here, this is called a partial trace because we are taking an operator in the composite Hilbert space, rho AB, and then we take the sum of diagonal elements, but in quotation marks, because it's only in the B Hilbert space. And we're only summing over the JB. We sandwich rho AB between the JBs. The result of this so-called partial trace is an operator in the A Hilbert space. So this is denoted as a trace rho AB, and to make clear that this is a partial trace that we're taking only in the B Hilbert space, the trace gets the subscript B. And this is then an operator in the Hilbert space of subsystem A. So this whole object here. With this notation, we can write this in the form, it's the sum over IA. What remains is the basis vector IA. Then we have this partial trace, trace B rho AB. Then we still have XA, and then we have IA. And here we again have a trace because we are summing over the diagonal elements in the A Hilbert space. So this in turn we can write as the trace in A over trace B rho AB XA. And again, we have the structure that we've encountered so many times before, that the expectation value of an observable XA is the trace over something times xa. And the something in the round bracket is the reduced state of subsystem A. And so here we have the general prescription that tells us when we have an arbitrary state for a composite system, we are looking for the effective or reduced state of a subsystem. Then the way we calculate that is that we take the partial trace of the density matrix for the whole system, and we take the partial trace in the Hilbert space of the other system that we are not looking at, and what remains is the reduced state of the subsystem of interest. I would like to illustrate this with a simple example. Let's take as an example 2 spins again. This is an example where the composite system is in a mixed state. And it looks as follows. Rho AB is a linear combination. Remember that any mixed state can be written as a linear combination of projection operators. And in this case, this looks as follows. Rho AB is 1/4 times the projection operator onto the pure state psi AB plus 3/4 times the projection operator onto chi AB, where the pure state psi AB is a superposition. It's 1/√2. And then, because it's a little bit faster to write, I would like to switch from this spin-up, spin-down notation to the 0, 1 notation. So I will use basis vector 0 to indicate spin-up, and I will use basis vector 1 to indicate spin-down. So the pure state psi AB is the superposition 0, 0 plus 1, 1. I think that's the same state that we encountered in the previous example, where we also had a linear combination of up, up, and down, down. If in the density matrix we only had the projector psi, psi, then it would be the same state that we had discussed before. But now we have a weighted average. 1/4 it's this psi psi, and 3/4 it's chi chi. And for chi AB, we use the state 0, 0 or up, up. Notice that psi and chi are not orthogonal, but that's not necessary. There's no need why the pure states or the projectors appearing in this linear combination for the density matrix, there's no need that they must correspond to orthogonal states. Okay, now we wonder what is the reduced state of subsystem A. What do we have to do? Rho A is the partial trace of rho AB, the partial trace taken in the Hilbert space of the other spin, namely spin B. What is that? It's the sum of the diagonal elements in Hilbert space B. So we have to be careful that we always carry the indices A and B now. So let me write the basis vector 0 with an index B, so for spin B, rho AB, 0B, plus 1B, rho AB, 1B. Then let's insert the form of the density matrix. And we get 1/4. Then we have 0b psi AB, psi AB, 0b, plus 1/4 1b psi AB, psi AB, 1b. And then we get the other terms, and we have 3/4 0b chi AB, chi AB, 0b, and the rest. Now let's look at these terms individually. Let's first look at this term here. Psi AB is this linear combination of 0, 0 and 1, 1. When you take the scalar product with the basis vector 0 in the B Hilbert space, remember the rules for the scalar product. When I take the scalar product of 0b with 0, 0, well, 0, 0 is 0b tensor 0a. Then I take the scalar product individually of 0b with 0b, so it's the two vectors living in the same Hilbert space, but this is 1 because it's a normalized basis vector. And what remains is 0a. Yeah? So perhaps I write this separately. So for example, we have 0b with 0, 0. This is a shorthand really for 0b, 0b tensor 0a. Now scalar product of 0b with 0b, that's 1 because it's a normalized basis vector, and what remains is that this is equal to 0a. I'm sure this is again not a mathematically very precise notation, but I hope you get the idea. So, coming back to this term that we have in this linear combination, so we have the scalar product of 0b with psi, and then we get a contribution from the scalar product with the 0, 0 term, and this gives 1 over square root of 2, 0a. And then we have a contribution from 0b, scalar product with 1, 1, but the basis vector 0 is orthogonal to the basis vector 1, and therefore this gives 0. And this is what remains, 1 over square root of 2, 0a. The same here. What remains here is 1 over the square root of 2, and then it's the bra 0a. You can repeat the same exercise for the other terms. Here, in the same logic, what remains is 1 over the square root of 2, basis vector 1a, and here what remains is 1 over square root of 2, basis vector 1a. Let's look at the next line. A scalar product of basis vector 0b with chi. Now chi is just 0, 0, and the scalar product of these two gives us what remains is 0a, and here 0a. And finally, these terms, because 1 is orthogonal to 0, this gives 0. This is equal to 0. So we can evaluate these expressions. So the first contribution is 1/4. Then we have twice 1 over the square root of 2. That gives us 1/2. 1/4 times 1/2 is 1/8. So the first contribution is 1/8, 0a, 0a. The second contribution is again 1/8, 1a, 1a. The next contribution is 3/4, 0a, 0a, and the last term was 0. So altogether we have 7/8, 0, 0 plus 1/8, 1, 1. And this is the reduced state. That finishes finally the discussion of composite systems and reduced states. I had promised to you that there is a final reason why we should work with mixed state. And this final reason is a conceptual result. It's a formal mathematical result that says that density matrices are the most general form that a physical state can have. In the following sense, consider, I'm not going to prove this theorem, I'm just going to state it, and those of you who are interested, perhaps more in conceptual or mathematical issues, I encourage to look that up. It's known as Gleason's theorem. Let's consider the following situation. You have a d-dimensional Hilbert space, complex Hilbert space, and the proof of the theorem only works if the dimension of that Hilbert space is at least 3. Remember our discussion of projection operators and where you encounter projection operators and how you can interpret projection operators, what meaning they have. There's a one-to-one correspondence between a projector and a subspace of your Hilbert space, namely the subspace onto which the projector projects. And so there's a one-to-one correspondence with a subspace of your Hilbert space. Now, for every subspace of Hilbert space, you can construct an observable such that the subspace is an eigenspace of that observable. And so there's a one-to-one correspondence also with the eigenspace of some observable. Take the one-dimensional case, a one-dimensional subspace. I can always construct a Hermitian operator that has an eigenvector which spans this one-dimensional subspace. When I have this observable, then I can of course characterize this eigenstate or eigenspace also with the associated eigenvalue. I can say this is the eigenspace corresponding to measurement outcome eigenvalue AI. Yeah? So in this sense, an eigenspace always corresponds to some measurement outcome. So with this chain of correspondences, we can say that a projector corresponds to a measurement outcome. And we had seen this before when we discussed projectors. We said the probability of finding a certain eigenvalue when we do a measurement is the expectation value of the projector, which projects onto the eigenspace that belongs to this eigenvalue. So already there we had found a correspondence between measurement outcome, or eigenvalue, and projector. And here it's just written down in a slightly different form. Now we can say, what is a physical state? Very generally, a physical state is a mathematical object that assigns to each possible measurement outcome a probability. That's the most general way you can define a physical state. So a physical state is some probability measure, prob of measurement outcome. That's the most general way you can introduce a physical state. However, you would like to impose some sort of minimal, some very basic consistency requirements. So you expect that this probability measure should satisfy a number of very basic properties. One of them is the sum rule. If I measure a certain observable with different possible outcomes, then I expect that the sum of the probabilities of the various outcomes is equal to 1. Another requirement, and this now gets rather technical, and I'm not going to go into this because otherwise this really becomes a course in quantum mechanics. But I just want to note it, that this is one of the assumptions in the proof of Gleason's theorem, the so-called non-contextuality. And just a few words what it means. Well, you can measure a physical observable together with any other physical observable as long as the associated observables, operators, commute. You know that from quantum mechanics. If you have two observables that commute, then you can measure them jointly, you can measure them together. Now let's say an observable A commutes with observable B, and therefore you can measure A together with B. Let's say that A also commutes with C. Then you can measure A also together with C. Non-contextuality in this setting here says that the probabilities that I assign to the possible outcomes of A do not depend on whether I measure A together with B or I measure A together with C. So they do not depend on the context in which I measure A, whether together with B or together with C. That's non-contextuality. And finally, there are technical requirements such as some form of continuity that I'm not going to go into. Then Gleason proved that a probability measure that satisfies these very basic requirements must be of the form probability of X, where X is a measurement outcome, must be of the form trace of operator rho times the projector associated with the measurement outcome X. So this is the associated projector, and rho is a density matrix satisfying the properties that we had listed before, of normalized, Hermitian, non-negative, etc. So in this sense, indeed, the density matrix is the most general form of a state that satisfies these very basic requirements.